Welcome back, folks. This is lecture number 9. As we get started, I wanted to talk to you about something. I wanted to talk to you about the rhythm of the class. It goes something like this. We have your performance as a function of time. So here you were. You started on day number 1. You thought, all right, this is going to be good. We're going to learn about electronics. And for a while, it was pretty good. But then we turned a corner. And then we keep going. And right now, you have fallen into the pit of despair. Not exactly a fun place to be, because it turns out that things are hard here. Things aren't quite making sense. You have lots of ideas, you have lots of vocabulary, but all the puzzle pieces aren't fitting together, or you could say the gears are clashing as you go on. Let me tell you something. This is normal. We are learning a new language, and it is getting hard. There are many concepts, and they're not all making sense. You have 2 choices to make. You could walk away from the class, in which case electronics will always be something that's just too darn hard, something out there. Or you could accept that maybe this is okay. It's not fun. I get it. It is not fun right here. We'll even write that. Not fun. But at least it's something that can be done. And what will happen is if you take that attitude, over time, you will reach this point here. And it'll take a good month. I'm not going to lie to you. But you'll reach this point where we start talking about motors and generators, and things will start to come together, and it will make sense. What I'm trying to say is that I recognize that this is frustration. It's a normal part of learning. Give it some time, work with your classmates, come to the study halls, ask questions, work the homework problems, review all the material that we've already covered, and see if you can get yourself to the point where it's not fun, but at least it's starting to make sense. And then keep powering through the pain, and I do believe that you'll come out the other side a very happy person. Let me give you an example. We talked about series circuits, and our circuit looked like this. And you know what? That wasn't so bad. You could work those problems. That was a source, and you had an R1 and an R2, and with very little effort, you could calculate the source current, and with the voltage divider rule, you could figure out the voltage on, for example, R2. Not a problem. Recently, we introduced something called Thévenin. Well, that was a little bit harder, but in reality, it's not that much different because it's still a series circuit, except now we've separated this thing called load. So this is load out here, and you got your Thévenin voltage here and your Thévenin resistance there. In the near future, we are going to move to something called alternating current. Our sources become sinusoidal, and then we add things such as inductors to our circuit. We still have terminals A and B, and we still have some load out here. Again, you can see the layering. And if we continue on, we'll reach generators. Still a sinusoid. We have resistors and inductors. Then we have an output. Except now we're putting multiple things together. This is a 3-phase generator. So there's phase A, phase B, and finally we have the 3rd phase, our phase C with a resistor and an inductor. That's the progression. We start out with a series circuit. We move to things like Thévenin. We're going to cover AC soon, and then we're going to get to motors and generators. And I think we could plot each of those here. We could talk about series. We could talk about Thévenin. We could talk about AC circuits. And finally, we get to the motors and generators that we already mentioned. Well, that's enough about that. Just hang in there, folks. Work to get yourself out of that pit of despair, and I think everything will be just fine for you. We're moving on to a new chapter today. We're going to talk about transients. But before we do that, let's do a quick review. 1 watt-hour is equal to 3,600 joules. 1 joule is equal to 1 watt-second. On a somewhat related note, 1 horsepower is equal to 746 watts. Energy is equal to the product of power and time. We described energy as work, and we had a few different ways of looking at power. We could talk about power being the product of current and voltage. We could talk about it being current squared resistance, and we could talk about it being voltage squared divided by resistance. We covered a few other things in our previous class about capacitors and inductors. The schematic symbol for a capacitor was 2 metal plates separated by a dielectric, and the symbol for an inductor is a coil of wire. We have an equation for energy is equal to 1/2 the capacitance by the voltage squared, and for the inductor, energy is equal to 1/2 the inductance by the current squared. Make a note that this energy is in joules. And here is some conversions for joules. We finished last class by talking about the current as a function of time is equal to the capacitance by a change in voltage over a change in time. There's a similar equation for the inductor. We talk about the voltage as a function of time is equal to the inductance by the change in current over the change in time. In the previous class, we assumed everything was linear. For example, V of t is equal to L di dt. And you might have had a graph that looked like this, where we had a 0 to 1 amp change in 0 to 50 milliseconds. So again, this is time, and this is current. And it was linear, something like that. So in 50 milliseconds, we would change by 1 amp. Something to realize is there are 2 different sections in this example. For this period, di dt, that is the change in current, so that's 1 amp, so that's 1 over the change in time, which is 50 milliseconds. In this case, di dt is equal to 0.05 inverse, so that's 20. And at this point here, you'll notice that it's flat. So what's the change in current? And the answer is, well, there is none. It doesn't move up or down at all. So the numerator is 0, which means di dt is 0. So it doesn't matter how far we move over in time because the numerator is 0 in that case. Question for you. If di dt is equal to 0, do we have another word in our vocabulary to describe that? So if this was 0 amps, and say this was 10 amps, and I told you that for all time the current was 10 amps, what would you call that? Well, you would just call that direct current. It's an unchanging current. In fact, if you got your meter out and you looked at it, you would say this symbol right here with the 2 bars is for direct current, as opposed to this one with a sinusoid, which would be alternating current. So something to keep in mind. If that's what current looks like on that inductor, this is what the voltage looks like. As long as the current is steady, you'll find that the voltage will also be steady. In this case, the voltage will be the inductance, di dt. In this case, where it's the inductance, which I haven't given you, multiplied by 20, which is exactly what this equation here says. Note this point here. Again, we're talking about time, we're talking about voltage. When di dt goes to 0, the voltage on the inductor also goes to 0. Moving on, some new material. We're going to talk about RC and RL circuits. That's resistor capacitor and resistor inductive. For those of you with a physics background, I want to point out that there is an analogy between resistors and mechanical dampeners, capacitors and springs, inductors and mass. There's some interesting implications here because we know that a spring stores energy. We also know that energy is stored in a mass while it's moving. So we can talk about potential energy and kinetic energy. Something to think about. The capacitor stores energy, the inductor stores energy, but the resistor burns energy and gives it off. You also notice that the spring, when you compress it, will return that energy back to the system, and a mass that's in motion will also return that energy back into the system. Something else we should consider before we get started, and that is the thermostat in a room. Suppose that you had the thermostat set for 70 degrees, and you're feeling a little chilly, so you moved the thermostat to 75. As a function of time, it would look like this. And so we move time in this direction. We would say we were at 70 degrees, and then at time equal 0, you move the thermostat to 75 degrees. Before you adjusted that thermostat, we can expect the room to hover somewhere around 70 degrees. And the moment you adjust the thermostat, the room will still be at 70 degrees. Sometime later, we can expect the temperature of the room to increase and then settle out to a new value, hovering around 75 degrees. This change that we're describing is known as the step response. This is the commanded step. We commanded the system to go from 70 to 75, and then this is, in green, the actual response of the system. It took some time to make that transition from 70 to 75. This is the steady state temperature. This is the initial temperature. And this piece here is the step response of the system. You'll notice there's a certain amount of time associated with this transition, and that curve has a characteristic shape. As a thought experiment, you might want to consider this. Suppose you had your furnace, and the furnace malfunctioned. And initially we were at 70 degrees. What would the temperature of your house rise to? The answer is, it would do something like this, where this temperature here is the thermal equilibrium. It's when the amount of heat that the furnace produces is equal to the amount of heat that's lost to the outside environment. Suppose we went the other way, and right here our furnace was broken. We would expect the curve to do something like this, where we settle in on a final temperature that's equal to the outside temperature. So thermal equilibrium and outside temperature. At this point, we can start talking about capacitors. In particular, we're going to talk about something called a sourceless RC circuit. We start with a capacitor that's initially charged. That's not too difficult to visualize. Here's a capacitor that's initially charged, a very large capacitor. We know it's charged because if we take it and we connect up this buzzer, it should beep. We could also take the terminals like so and get a screwdriver across there. Okay, so it was initially charged. Not charged no more though. Okay, enough with the sparking. We have initially charged capacitor. This time we put it in a circuit with a switch and a resistor. So let this be R. And at time equals 0, we're going to close the switch. When we do that, we end up with a curve that looks like this. As a function of time, this is the capacitor voltage. Before time 0, the capacitor was charged to V initial. After the switch is closed, when the switch closes at time equal to 0, which is 0 right here, we'll see a curve that looks like this, where this is the capacitor discharging. You'll notice this is not linear. Okay, this would be an example of linear. You'll notice the capacitor discharging is not linear. In fact, this curve, the voltage on the capacitor as a function of time, could be described as the initial voltage, V initial, e to the negative t over RC. Or another way of saying that is initial voltage, maybe we'll use a big I there instead, e to the negative t over tau, where tau is this symbol here, is the product of the resistor and the capacitor. You should know that tau has units of time, actually seconds, which means we could go to this plot here and we could talk about time equal to tau. When time is equal to tau, you'll find that you are at 36.8% of the initial voltage. If you wanted to put a number on that, that's e raised to the negative 1. So if you go to your calculator, shift, that's way over here, so e raised to the negative 1. There it is, 36.8%. Let's work an example. We start with this circuit. We'll let this be 100 microfarad. We'll let the switch close at time equal to 0. And we'll let this be a 2000 ohm resistor. Remember this equation, the voltage on the capacitor as a function of time is equal to the initial voltage, e to the negative t over tau. You'll definitely want to put that on your note card. And again, this is for a sourceless RC circuit. So voltage on the capacitor is a function of time. We're going to let this be 50 volts. So volts initial was 50. So that would be 50 e to the negative t. Now we need to go figure out what tau is. So remember, tau is the product of the resistor and the capacitor. In this case, tau is equal to 2k by 100 micro. So we'd enter that as 2, and I'm going to use this button here, x, 10 to the x, and then we'll put a 3 there. So that's 2,000 times, and we'll do it again, 100, here's that 10, x10, to the negative 6, because that's micro. And the answer is that tau is equal to 200 milliseconds. So we come over here and we would say that's voltage on the capacitor is equal to 50. Oops, you can't see that past my head, can you? Try that again. Voltage on the capacitor is a function of time, that's a bad t there, is equal to 50 e to the negative t over 200 milliseconds. Or another way of saying that is we invert this number. So Vc of t is equal to 50 e to negative 5t. And all we did there is we took this 200 milliseconds and we moved it upstairs, which might make it a little easier to solve the problem. Remember that this equation describes a line where we had time here, and we had the voltage on the capacitor, and we see that the voltage does something like this. When time equals 0, we'll see that the voltage here is 50. We could say this here is Vc of 0. What is, so we're going to find, what is the voltage on the capacitor at, say, 75 milliseconds? That is equal to 50 e to the negative 5 times 0.075. Let's even work that out. So 50 times e to negative 5 times 0.075. So the voltage on the capacitor at 75 milliseconds is equal to 34.4 volts. Going back to the chart, if we were to walk over by 75 milliseconds, we would find that the voltage there is 34.4 volts. We could work this problem the other way. Suppose we're told that the voltage on the capacitor as a function of time is equal to 25. Solve for time. In that case, we'd use this equation again, except this time we'd set it equal to 25. So 25 is equal e to the negative 5t, and we need to solve for that t. So working our math here, 0.5 is equal to e to the negative t over 200 milliseconds. If you remember your math, you'll know we need to use the natural logarithm to break that negative t over 200 milliseconds out of jail. Natural log of 0.5 is equal to natural log of e to the negative t over 200 milliseconds. So we come over here, natural log of 0.5. That gives us negative 0.693 is equal to negative t over 200 milliseconds. Solving for t, we end up with 140 milliseconds. So now we could come over here and we would say that at 140 milliseconds, our voltage is at 25 volts. By the way, if you forgot, the natural logarithm of e to the x is equal to x, and also e to the natural logarithm of x is equal to x. So keep those two rules in mind as we continue on. That was an example of a sourceless RC circuit. Again, there is no battery in this circuit. The capacitor is what held the initial charge. What we're going to do now is move on to charging a capacitor. We start with a power supply. We'll let this be 5 volts. We'll close the switch at time equal to 0. We'll let this be 10 kilo ohm. And we'll let this be 330 microfarads. And for our purposes, we're going to let this be initially uncharged. For your note card, the voltage on the capacitor as a function of time is equal to the final voltage plus the initial voltage minus the final voltage, e to the negative t over tau, where tau is this symbol, which is also the product of RC. In this example, tau is equal to 10K by 330 micro. So tau is equal to 10K by 330 to the negative 6. So tau is equal to 3.3 seconds. Using this equation, we would say the voltage on the capacitor as a function of time is equal to the final voltage, which will be 5, I'll show that in a minute, plus the initial voltage, which is 0, minus the final voltage, which is 5, e to the negative t over 3.3 seconds. If we simplify that, it looks like this. So it's 5 times 1 minus e to the negative t over tau, which we said was 3.3 seconds. Now that we have this equation, we can plot it as a function of time. So here we have time, and this is voltage on the capacitor. The curve will look like this. It will increase steady at first and then level out. It levels out to the final voltage, so V final, in this case, is 5 volts. There are a few points you should be familiar with on this curve. One of them is time is equal to tau, and we describe that as the product of RC, so that's 3.3 seconds. So in time equal tau, which is 3.3 seconds, we will be at 63.2% of final. So 5 times 0.632 is, we'll be at 3.16 volts. Be sure you put this on your note card. When you are charging a capacitor, you will move to 63.2% of the final voltage in one time constant. That's not to be confused with our sourceless circuit. On our sourceless circuit, you will drop 36.8% in one time constant. There is another one you should remember, and that is out here at 5 time constants. For this circuit, you'll be fully discharged in 5 time constants. In this circuit, you will be fully charged at 5 tau. So again, 5 tau is considered fully charged. Let's work 2 more examples and then we'll call it done. As you look at this circuit, this A and this B strongly implies that this piece here is either a Thévenin or a Norton equivalent circuit. We are going to convert that into a Thévenin first. The Thévenin resistance is equal to 1K in parallel with 3K, which gives us 750 ohms. The Thévenin voltage can be calculated with a voltage divider as 1K over 1K plus 3K by 100, which gives us about 25 volts. From there, we redraw the circuit. 750 ohm, 25 volts, switch closing at time equals 0, and this 10 microfarad capacitor. Tau is equal to the product of RC, which in this case is 750 by 10 microfarad. So that's 750 times 10 microfarad, which gives us 7.5 milliseconds. From there, we need to go find that equation you wrote on the note card, which is this one here, and then we apply it. Using that equation, the voltage on the capacitor as a function of time is equal to the final voltage, which is 25, because that's what we're charging it to, plus the initial voltage, which we'll assume is 0, minus the final, multiplied by e to the negative t over 7.5 milliseconds. That can be simplified to 25, 1 minus e to the negative t over 7.5 milliseconds. And from there, you could do the calculations to determine the voltage at a particular time or the time for a particular voltage. I hope you see the pattern here. Given some complicated circuit, you need to calculate the Thévenin equivalent, right? So you have some A to B, and to that, you're attaching the capacitor. So again, there's your Thévenin circuit. Thévenin voltage, Thévenin resistance. All right, so simplify all of this into a Thévenin circuit, and then think of the capacitor as the load that's being charged. One more example. This time, we'll do a resistive inductive circuit. You should know that tau is equal to the inductance divided by the resistance. Also know that the current on an inductor as a function of time is equal to the final current plus the initial current minus the final current, e to the negative t over tau. This equation is similar to the one we just did for the capacitors, except this time we're substituting in current for voltage. Let's assume this circuit. We'll let the switch close at time equal 0. 50 volts, 75 ohms, and 2 henries. The time constant tau is equal to L over R, which is 2 over 75, which gives us 27 milliseconds. We need to go on a short sidebar here. When we looked at the voltage on a capacitor as a function of time, we said that the final voltage on the capacitor is the source voltage. Right, so the capacitor is charging up to volt source. The inductor, we're dealing with current. And we end up with the same curve as you saw from the equation, but the question is, what is this value here? To answer that, you have to go all the way back to the beginning of the lecture. We talked about the voltage on an inductor as L di dt. You need to consider this piece here. So what is the change in current at that point? And the answer is, well, it's not. Right? There is no movement in this direction. So the change in current is equal to 0, which means the voltage is equal to 0. And if we were to add that curve, this is the voltage curve. So this is voltage. By the way, we should do the same for the capacitor. So this here is the current curve for the capacitor. Again, this is talking about capacitors. This one is talking about inductors. So there's no confusion. Remember that this is the voltage on a capacitor, and this is the current on the inductor. So when we ask this question, what is the current? What is the final current? Well, that final current also happens to coincide with a point where the voltage is equal to 0. As a takeaway, recognize that when the current is not changing on an inductor, you could say when the current looks like direct current on the inductor, right? No change in this direction, then the voltage must be equal to 0. And if you have a voltage of 0, isn't that the same as saying you have a short circuit? So if you come over here, conceptually, at time equals infinity, the inductor has become a short circuit. So the final voltage is a question of Ohm's law. It's 50 volts divided by 75 ohms. So now if we put that all together, we would say the current on an inductor as a function of time is equal to 50 over 75, 1 minus e to the negative t over 27 milliseconds. Finally, before we forget, we should say at DC, an inductor appears as a short circuit. We could also say at DC, our capacitor presents as if it was an open circuit. That is reflected in these charts here. As time approaches infinity, the capacitor is fully charged and the current goes to 0. Whereas the inductor, as time approaches infinity, the voltage goes to 0 and the current reaches some stable point. And that stable point that it reaches is the source voltage divided by the resistance of the circuit. When you come back for the next class, we're going to do something that's really interesting. We're going to take these concepts about inductors and capacitors and the charging and the difference between the current and the voltage. We'll start down the path of alternating current circuits that have resistance and inductance and capacitance. This gets us one step closer to that switchboard we mentioned in the first lecture, where we had those meters. We had meters for power, which was in watts, meters for VARs, we had meters for voltage and current, and we also had this thing called a synchroscope.